Good day and welcome back for the fourth part of our discussion on differentiating inverse trig functions. And I want to begin this video with the summary we had at the end of our previous video. So we should be familiar with how these three inverse trig functions are defined and the associated differentiation and anti-differentiation formulas. So I realize it's quite a bit of information, but as always, the more we practice, the more we think about these properties, the easier, the quicker, the more efficient it becomes. So in terms of practicing some examples, I find that the differentiation is usually easier for students sometimes than the anti-differentiation, just because differentiation is just so much more procedural or methodical. Based upon the form of the function, we immediately have differentiation formulas, say product rules, quotient rules, chain rules that we can apply. So with that in mind, I would like you to pause your video and differentiate the function f and the function g. So hopefully you've paused your videos, you've came up with derivatives for f and g. And let me just note once again, if you're not pausing the video and you're just thinking, gosh, I'm going to wait, he's going to start talking in probably about 5 to 10 seconds, you certainly can do that, but you get a lot more out of it if you think about it on your own first. That is a fantastic way to learn, especially in mathematics. When it comes to differentiating 1 over arc cosine, you could apply the quotient rule. I prefer to rewrite this as arc cosine raised to the minus 1. And then apply the chain rule. But either way works perfectly fine. So the chain rule tells us the minus comes down. The new power is minus 2, 1 less than minus 1. We substitute in that inside function arc cosine, and then we multiply by the derivative of that inside function, arc cosine. Which gives us minus, and I prefer to write it without the negative exponent, so we'll say 1 over arc cosine squared, but you could leave it in its previous form, times the derivative of arc cosine, which is minus 1 over the square root of 1 minus x squared. And you can leave it precisely in this form. To differentiate x arc tangent of x, we would want to use the product rule. And let's just write out directly what the product rule tells us, all in one step. Take the derivative of the first times the second, plus the first times the derivative of the second. So very quickly, very efficiently, we have these two derivatives. Now, what remains for us is an example involving an antiderivative. And what I want to note is that the antiderivative we see for 1 over x squared plus a squared is very similar to this arctangent formula we have above. And in fact, integrals of this form will be encountered frequently when we get to our next chapter, which is solely focused on integration. So it's really nice to have a formula now that can be applied later. So let's go ahead and see if we can evaluate this, and I'll give you my intuition along the way. To anti-differentiate 1 over x squared plus a squared, the idea is exactly where we started. We said, wow, this looks awfully similar to above. So the question is, can we somehow make it look just like that? And the key difference between the two is this a squared in the denominator. So let's go ahead and factor it out. So in the bottom, what we're going to do is pull out an a squared. So an a squared pulled out of that second term leaves us simply with a 1. To pull an a squared out of the x squared, that would leave us with an x squared over a squared. And I know sometimes at first glance it looks a little awkward maybe. It seems like we're actually kind of complicating the situation. But if you don't quite see that at first, note if you take this a squared and you distribute it through and let it hit each term, you're left precisely with that x squared plus a squared in the denominator. So you're wondering, why would we do that? Well, we have 1 over a squared, which is a constant we can pull in front of the integral, and what we're left integrating would be 1 over the quantity x over a quantity squared plus 1. And what I want you to think about, and if you need to, pause the video for 30 to 60 seconds and think, what technique of integration do we have that can make this integrand precisely turn into this above integrand? And hopefully what you're thinking is a substitution. If we can let u be equal to x over a, du is 1 over a dx. Remember, a is just representing in this problem an arbitrary constant. So to finish writing our integrand in terms of u, simply note a times du is dx. So a is a constant in front of the du, which we can pull in front of our integral. And when we do that, we would have an a that we pulled out, and then dividing by the a squared, which is already there, integral of 1 over u squared plus 1 du. So the a cancels an a off in the bottom, and we have a 1 over a out front. The antiderivative of 1 over u squared plus 1 is arctangent of u plus c. And now we have our formula of interest. Resubstituting back in that u is simply x over a, we have 1 over a arctangent x over a plus c. And just to summarize, because this is a key formula that we will encounter frequently moving forward, the antiderivative of 1 over x squared plus a squared, and note in this case a is a non-zero constant, and this is 1 over a arctangent of x over a. So from a pattern recognition standpoint, it has a nice form with the 1 over a, x over a. So once again, another formula to add to our list that we need to be familiar with. In the remaining video for this topic, we will go through another example involving an antiderivative, and then there will also be a class worksheet. So before going on to the next video, I would recommend go to Canvas, find that associated worksheet, and set aside some significant time to work through those problems. And in the next video, we will summarize several of them, but as usual, you can find the full typeset solutions on Canvas to compare your work with. So stay tuned. Take care.